Good morning. Welcome to Krishna's classes. At the outset, let me wish everyone a very happy New Year all over India, because this is called Vishu Day, Kerala. Assam, it's called Bihu. There are various names for it, and it is considered the uh, first day of the solar year. Okay, now let me begin with a new topic. What I intend to explore next is the very well known LP spaces, which plays a central role in mathematical analysis. And this is so especially the application to study of partial differential equations and so on. So let us start with the preliminaries. And one of the basic concepts that we take up is the so-called convex functions or convexity of functions. Now let us start with the definition. There are some preliminary results which are needed in the exploration of the so-called LP spaces. Define what are called convex functions. A real function means a real valued function defined on a segment AB, where minus infinity A less than B less than or equal. That means it could be, the interval could be infinity to minus infinity. So that's the whole real line. That's what it is. That's why this equality is occurring in the restrictions for the choice of A and B. Is said to be convex. Convex if phi of 1 minus lambda x plus lambda y is less than or equal to 1 minus lambda y whenever A less than x less than b, less than b, A less than y less than b, and so the evaluation of phi at 1 minus lambda times x plus lambda y is less than or equal to 1 minus lambda times phi of x plus lambda times phi of y, where lambda lies between 0 and 1. A and x and y are, you have A, P, this is a segment. that we are looking at. X and Y are 2 points here. Maybe X less than Y or Y less than X, it doesn't matter. So this inequality is satisfied. Okay. Now let us explore this. Let us try to understand this geometrically. Then it is much easier to get a feeling for what is meant. So geometrically. Let for whatever t, this phi is defined. Okay, so t lies between minus infinity and plus infinity in general. Okay, that means it's in R2 t, then it's a graph of the locus of the point t phi t is what you call the graph of phi. Okay, so the locus of graph. Now what does this say? So you see, you have, suppose this is the point A, this is the point B, or this is the point X, this is the point Y. Then you have X, YX, Y, Y. Now, if you join these 2 points by a line, okay, then what are the points on this? Join the 2 points on it. If you take an arbitrary point, now an arbitrary point on this is then t phi t, where t lies between x and an arbitrary point on this line is essentially this point is t or this is equal to lambda minus 1 minus lambda lambda. Or you can write it as 1 minus t x plus ty. Okay. So by changing by lambda, when lambda is equal to 1, you get the point y. When lambda is equal to 0, you get the point x. So all intermediate points on this line are given by 1 minus lambda x plus lambda. Okay. So suppose t is equal to lambda y, right? Then the corresponding point on the line y phi y is given by is 1 minus lambda x lambda y. This is the point. Comma y 1 minus lambda phi x that is this point. You want to call this q. Suppose S is the point. Then S has coordinates joining Wi-Fi. Lambda y. The corresponding point on the graph of is, what is it? T by T. Okay, that is that is Okay, so this is the point. Now look at the, so what we obtained is phi t is less than or equal to, then the definition of convexity is phi requires phi t to be less than or equal to, less than or equal to 1 minus lambda Okay, geometrically what it says is that this is the point, yes, that is the point R, which is t phi t, lies below the point S along the same vertical. Okay, that is phi of, what is t? T is 1 minus lambda less than or equal to phi. So that is the definition for this is the meaning of convexity. That means this height is less than or equal to this height is actually 1 minus lambda phi x plus lambda phi. So this point is 1 minus lambda x lambda y. Now this height, so if we designate t by 1 minus lambda x plus lambda y, then the point S is essentially 1 minus lambda phi x plus 1 minus lambda. So what the theorem or what the definition says is that the point R is straight away below the point along the same vertical line. Okay, so that the height that you have, if you call this A, B and C, the height CR, that is CR, CS, that is the, okay, so that is what you mean by convexity. Now the same thing can be reformulated as as follows. A less than S, B, we have phi t minus what does this say? This says the following. It's a different interpretation. So this is A, B. This point is A phi A. This point is now for points T and S and U. Okay, so we have chosen S, we have chosen T, chosen the point. Now what is C? This is the graph of the curve. And this is, then you say it is convex. So what you need is this one. This is the height. Now you take this line and take this line. What is the slope of this line? So let us mark these points, name these points. So this is A and this is B. This let us take and R. Okay. So slope of PR is, what is that? Phi t minus slope of RQ is phi u minus phi t divided by okay. So what you ask for is that the slope of the line R is less than or equal to slope of the line, or it actually bends upwards. Okay. So slope of R for every choice of P, Q and R satisfying the given conditions. That means for every choice of S, T, U such that A less than S, less than T, less than U, less than. Okay. So this is another way of understanding what convexity is. Now designate this by, and what is that? Designate phi of this, right? Okay. The mean value theorem for differentiation along with two, that is this inequality, shows that phi dash at a real differentiable function, if phi is real differentiable function, and convex, then what you have is this: phi dash s is less than or equal to phi dash. So these are the conditions. Applying mean value theorem, assuming that the function phi is a differentiable function and convex, then from this inequality proceeding to the limit, we get phi derivative at s is less than or equal to phi derivative t. Okay, so that is obtained by taking the limit on either side, but we need the condition that the function is a differentiable. What does this mean? That means the derivative, in such cases, the derivative is a monotonically increasing. That is, in such cases, phi derivative is a monotonic increasing function. Because convexity does not require the differentiability of the function, but in this special case of phi being differentiable also, then you have the convexity means that the phi derivative is a monotonic increasing. Now you can take the examples. On for x belonging to minus infinity plus infinity. Just recall the graph of exponential. 2 infinity. Now these are all examples of convex functions. Okay. Now you can examine what happens to the function fx equal to x to the power n if you consider it on the line on minus infinity to 0. Okay. So question. Minus infinity to that will give you some more insight to the concept of convex. Now, one of the results that you can immediately prove is that if phi is convex, it's continuous. We have the following theorem. If convex on AB continuous only. Now we give a geometry. May not appeal to some people as a rigorous proof, but you can recast the whole thing using epsilon and delta arguments to show that if phi is convex on AB, then it is continuous on. Okay. So we make use of the geometry. Geometry. Suppose so A less than X, S less than X, less than Y, less than P, and less than now phi is a convex function. Something like, I mean, this is the geometry. This is what the geometry says. The behavior of the function. Okay. So let S S comma X the point Y the point and E be the point. Right. So these are the 4 points. Okay. So this is yes, and yes. These are the coordinates for this. This is x by x. This is y by y. This is t by t. Okay. Now you join the line S to Y. Okay. Then function phi is convex if the point X lies below the line SY. The line, the point X is below the line SY. This is your SY. Also, Y is below the line XT. This is the line XT. This is the line XT. So this lies below. It's the point Y. X is below the line Y. Y is below the line XT. These are the geometric inferences from the definition of convexity. Now Y is on or above the line Sx. This is Sx. See, this is the line we are talking about. This is above. So y is on or below this is xt. Y is on or below xt. Y is on or above the line 6. Now let tend to x. That is the point y tends to x. It is this ordered pair. As y tends to x, then the point capital Y tends towards x, capital X, which implies, and that is y tends to phi x. The left hand limits are handled in the same way. In the same way. Okay. Then what you get? See, this is the slope at x, this is the slope at y, to take the limit. So the slope of the tangent to the curve at y is greater than or equal to the slope of the tangent at x. Okay, so that's what we assert. What does this mean? As we have seen, as y tends to x, phi y tends to phi x. Similarly, as y tends to x, now as x tends to y, phi x tends to, okay? Or you can fix a point and then take the now what we do next is this. We make some remark. If the function has a discontinuity in the interval AB, some point okay, so this is easy to see. So that is the first rule. Now how do we, so let us look at some example. So let's suppose this is the function. Okay. Suppose phi at t minus is strictly less than that means the function has the value here. This is a by a b. Now what one does is you choose okay, then you have phi, right? So what can you say about one minus lambda lambda phi? Okay. Now you see that this is going to be somewhere take this some point. So let us take tangent. Okay. Now choose a point. So let now let us take this. Right at x where okay, right, and phi x is x minus. That means it is clearly a jump discontinuity. Now take the point. So take s less than x and t greater than the line segment joining t phi and s phi s has the property that phi at x is above the line phi of x is this. So in fact there are several points where this phenomena occurs. Okay. Therefore phi is not complex. What does this mean? This means suppose x is equal to then phi x is equal to this is the point x phi x. Then phi x is less than or equal to therefore it is clearly not convex. Similarly, suppose phi is continuous at x from the left and not from the right, then one can show choose less than the convexity is finite. So discontinuities in between. So discontinuities, so if phi has a discontinuity on the open interval AB fails to be convex. But there is a situation where the discontinuity would give you still retain the convexity. So example 2. Consider the example. And phi 1 equal to convex in spite of the fact phi has a discontinuity at the end point 1. Okay. So on any open segment, you cannot have discontinuity for a convex function. So on any open segment, a convex function cannot have discontinuity. Anywhere. Open interval A. But suppose it is at the end point, the boundary, then it doesn't matter. Okay, so that is the significance of the example, right? So I stop here and we'll continue with the further results or some nice inequalities which we require to prove certain results on NP. The next theory.